Okay, welcome people of the pre-seminar. It's a pleasure to have Aaron Kettner, who's a local here in Prague, and he's going to tell us something about groups, C-star algebras of torsion-free, virtually abelian groups. Please.
Yes. Thank you. I hope the microphone is on. I think so. Okay, great. Let me start by defining the object that I'll be talking about. So let G be a discrete countable group. Will be throughout the talk, discrete countable group, and consider the left regular representation. Lambda, which is a representation of G on L2 of G. And how does it operate? So lambda G sends EG to EGH. Oh, sorry, H to EGH, where the EGs form the canonical orthonormal basis for L2 of G. Okay, yeah, that's as usual, I guess, the left regular representation. I would assume everybody has seen that before at some point. And now we define a C-star algebra to basically be generated by, well, it's basically the C-star algebra generated by the image of lambda inside B of L2 of G. But actually, it's enough to just take the closed linear span of the image. So we take the closed linear span of the image of lambda. And yeah, you can check that this is even closed under multiplication and closed under involution. And so it's a C-star algebra. And we call it the reduced group C-star algebra. Of G. Okay, and maybe for the algebraists in the room, which might be in the majority at the moment. So I would think of this as a C, or it is a C-star completion of the group algebra. C of G, which is generated by some elements indexed by the group with relations delta G, delta H is equal to delta GH for all G and all H and G. So yeah, that's really what this is. So again, for the algebraists, think of the algebra over the complex numbers generated by basically the group elements subject to the obvious relation. And you can turn this into a star algebra by defining an involution, and you can then take a C-star completion, and that's exactly what we've done here. So we obtain a C-star algebra. And for finite groups, at least, this is very intimately, the group algebra is very intimately related to the representation theory of the group, right? And the same is true for the group C-star algebra. So this is somehow an interesting object that has been studied for a long, long time. It's also, in general, very difficult to understand. A lot of deep results about when this is simple, for example, or about its K-theory, which is exactly the Baum-Kohn conjecture, right, about the K-theory of this group C-star algebra. So this is my point is that this is an object which is very important to understand, but it's also very difficult to understand in general. And we will be looking at this for one specific class of groups. So namely for these torsion-free virtually abelian groups. So what does that mean? We call G torsion-free if for all G and G, G to the K can only be the identity for some K in the natural numbers with 0 if K is actually 0. Wait. For algebra implies K. And we call G torsion, not torsion free, virtually abelian. If it contains a finite index abelian subgroup, and just to spell this out a little more explicitly, so this means that N, well, it's a subgroup of G, and it's abelian. Okay, sorry. In a second, it will be a normal subgroup, but yes.
So the top one, I guess, G would also be 1.
What?
Like if G is 1, then G to K is also 1 for K.
Okay, so maybe I should say that this should be without the identity, right?
Yep.
Thanks. Right, so we call G virtually abelian if it contains a subgroup N which is abelian, and it has finite index, meaning that if we define H to be the quotient of N of G by N, then this is finite. And now there is a fact about virtually abelian groups, apparently, that you can always choose N to be a normal subgroup and to be maximal abelian. So we can choose N to be, first of all, normal, meaning that H, this quotient, is actually itself a group. And secondly, you can choose it to be maximal abelian. Meaning that it is not properly contained in any bigger abelian subgroup. Okay, so we have this, we start with this assumption, virtually abelianness. Then we obtain a normal subgroup, which is abelian. And from that, we obtain a short exact sequence of groups. And now basically the idea is, okay, we have the subgroup, we have the quotient. We can somehow reconstruct G from the subgroup and the quotient. And then this also tells us something about the group C-star algebra. Okay, so let me go through this. So what data do we get from this short exact sequence? So first of all, we define an action on H on N. We define theta, which goes from H to the automorphisms of N. And it's defined by a conjugation with elements in H. So for N and N and H and H. And now, just to prove something, I will prove the following lemma. namely that theta is actually well defined. And it is an action of H on N. What does that mean? What do I have to show, right? Why would this not be well defined? Well, what is this actually? Like, what multiplication is this here? Because I've taken an element from H, which is the quotient, and I want to multiply it with an element in N. And I can do this inside G, right? So I can pick for each small h in big H, I can pick a representative in G, and then I can use this to do this multiplication, but I need to show that it's independent of what representative we pick. So we have to show for well-definedness that if I take H1 and H2 and H such that they have the same image under the quotient map, which I want to call pi. So pi of H1 is equal to pi of H2. Then we need to show that they define the same map up there. So theta of H1 is equal to theta of H2. Okay, so what do we get from this sort of immediately? We get that pi of H2 inverse H1 is equal to the identity. Now, the kernel of pi is exactly our normal subgroup N. So this means that H2 inverse H1 lies is equal to some element M in N, which now means that H1 is equal to H2 times M. Now, what I have just shown basically is that these equivalence classes are cosets, right? But you can always write them like this. Okay, so now we just plug that in. So this means that if I take theta of H1 of N, then by definition, this is H1 and H1 inverse. Now I plug in this formula, then I get H2 M N M inverse H2. And now N is abelian. So that's crucial in this step because these commute, and this is M inverse, this is M, so they cancel out. So this is H2 N H2 inverse, which is just theta H2 of N. So this works. This is indeed well defined. So that means this is a well-defined map. The other thing is this actually an automorphism of N? So does it preserve the normal subgroup? And well, it does because it's a normal subgroup. So for all H and H, theta H of N is equal to N simply because N is normal. Right, because by definition of a normal subgroup, it's preserved under conjugation. So this is all fine. And now is it an action? Yes, it's an action, which is also clear, I would say. So H1, theta H of the identity. Well, if you plug that in, you conjugate, so this the H cancels, just get the identity. And similarly, it's very clear that if you first apply theta H2 and then theta H1, you get the same as theta H1, H2. Okay. Okay, so we have this action. Now there's one more piece of data that we need to get from this short exact sequence, from this extension, that will allow us to reconstruct G, which is a cocycle. So what we do now, we take some section. So some map, so here we have pi, right? So if now I have a map from H to G, which I called S, so that if we first apply S and then we apply pi, we get the identity on H. And you can do this if you don't ask S to be a group homomorphism. You cannot always get a group homomorphism which does this. Then the extension would be trivial. But you can do this if you just take a set theoretic lift. So this is not in general, it's not a group homomorphism. Okay, so then we can do this. You just go through the elements of H and you pick you pick any element in the pre-image of that H. So that works. And now we define our cocycle, which is the map from H to H into N. Which is defined in the following way. Which is a 2 cocycle. So first of all, this indeed lies in N, the right-hand side, because, well, N is exactly the kernel of pi. If I apply pi to this right-hand side, the S just vanishes, it disappears because of this condition, right? And so you see that the right-hand side will be the identity after applying pi. So, and then it has a bunch of properties which I don't want to write down, but which make it a 2 cocycle. And
measures the failure S being.
Yeah, exactly. So if S was indeed a group homomorphism, then this would be the trivial. Yeah. Thanks. And now we define the group, just like the twisted semi-direct product, I guess, N by H to be just the Cartesian product as a set. With multiplication given by following N1, H1, H2 is equal to N1 theta of H1 of N2. And then you multiply with omega of H1, H2. Okay, this is the first component. So rather than just multiplying the first two components, you apply theta to the second one, and then you also have this cocycle floating around. And then in the second component, we have H1 times H2. So we define this group, and then it turns out that G is actually isomorphic to this group. Right. So if you've seen group cohomology before, then this will be familiar to you, because what we have done is just we have started with an extension, and then we have produced a cocycle. And this cocycle will give you, maybe I do this as an aside. So this cocycle would give us a class in the second cohomology group of H with coefficients in N, where you have to fix the action. So the action that we constructed up there, the theta, this is part of the data now. Right, so this cocycle gives you a class in here, and then elements in this H2 classify extensions up to some reasonable notion of isomorphism. So yeah, this is not a surprise at all. There's a lot of deep machinery which sort of has been developed for these sort of extension problems. And yes. And for that reason, also the opposite way works, right? So it's not only that we can take an extension and produce such a co-cycle, but it's also that given a co-cycle, you can actually reconstruct the group, and not only the group, but you could also reconstruct the extension, so the quotient map pi. Okay, so now we have taken our group, the group that we started with, and we have written it as such a twisted semi-direct product. And now this, tells us something about the structure of the group, right? Like this sort of tells us that we have decomposed it in some sense into two hopefully easier to understand subgroups. And now we want to do the same with the group C-star algebra, which is our actual object of study. So now it's not too far-fetched to hope that something similar works on the level of the group C-star algebra. And indeed, that is the case. So now I'm going to define the twisted cross product, but in a very vague way. So take this C-star algebra, which we call the twisted cross product. This should denote the C-star algebra. Generated by elements of the group C-star algebra of n on one hand, and unitaries UH or H and H with the relations Okay, so again, I'm appealing to the algebraists in the crowd, so I don't want to make precise how you actually build this C-star algebra, but I would just think of it as the algebra generated by elements of this guy and by a bunch of unitaries indexed by elements of H, such that a certain number of relations are fulfilled. Now, what kind of relations would we want? We would want to know how these unitaries interact with each other. Sorry, yes, good question, thank you. So this is generally in a C-star algebra. Let's say A is a C-star algebra. Then you have this involution, right? Which is like the adjoint, taking the adjoint of an operator. And unitary, this would be an element where its adjoint is the inverse, the multiplicative inverse. So we want that U star U is equal to U star is equal to the identity of A. Now assuming it's unital. Okay, so this is think of unitary matrices really. That's the idea. Or unitary operators, if you like operators. Right, so how do these unitaries interact with each other? If I multiply UH1 with UH2, I can almost commute them, but not quite, because I get a factor that depends on the co-cycle. So what do I do? Okay, here I have the unitaries just turned around. And here I take delta. Remember that delta was one of these unitaries inside C star reduced of G, of N. Right, so the co-cycle omega takes values in N. So this is the element that is associated to this the image of the co-cycle at that point. I hope that's clear. So yeah, you multiply that to the unitaries. And now the other question is, how do elements of this C-star algebra interact with the unitaries? That is the other type of relation. And they do that in the following way. If I take UH, one of the unitaries, and then I take delta N, which again is one of the unitaries in here, since the reduced C-star algebra of the normal subgroup, then you see the action. So now you can commute them, but you need to sort of change the index here. You need to change the n. Okay, I hope my notation with the delta and the u is not too confusing. If you get confused, let me know. So this is this cross product. Now again, I mean, I'm talking about the algebra generated by these elements with certain relations, but of course you again have to take some C-star completion. And in general, it would matter which C-star completion you take, because there can be several ones already for our group C-star algebra that we started with. But virtually abelian groups are always amenable, and for amenable groups, all of these completions are the same. So it doesn't matter. Like here, I have phrased it in somehow a more universal way, saying it's like the C-star algebra generated by these guys, and then you could take like a universal C-star completion. Over there, we have taken the closure with respect to some representation, so that's like the reduced guy, but it's really all the same. So I don't care too much about this. Okay. And now the proposition is that indeed this twisted cross product is isomorphic to the group algebra we started with. So we have an isomorphism of C-star reduced of G with this this cross product. And it's an isomorphism of C-star. Okay, so I hope you see the parallel to what happened to the group itself, right? The group was decomposed as a semi-direct product. The group C-star algebra can be decomposed as this sort of twisted cross product. Okay, and now I am well, not done yet, but close to the end. Now the whole point, sort of the punchline of this pre-seminar was supposed to be that we gain information on the group C-star algebra, and we already sort of have done that. We have gained information on its structure by writing it as such a cross product. And now we will see one consequence that this has. So there's the following proposition, which now for the first time is somehow in a more general framework than what we had so far. So if you just take an abelian normal subgroup, of a discrete countable, I guess, torsion-free group G, then the following are equivalent. First, C-star reduced of n is maximal abelian. In the group C-star algebra. Secondly, n is maximal abelian in G. And I mean, just for fun, I guess another equivalent condition is that the action of H on n that we constructed before is faithful. And an immediate corollary of this is that, well, if you do start with a virtually abelian torsion-free group G, then we have seen before that you can always choose n to be maximal abelian. So the second condition is always fulfilled. So that means that you actually get a maximal abelian subalgebra. Let G be a torsion-free virtually abelian group. Again, countable and discrete. And we know that there exists a maximal abelian normal subgroup. Then, I hope I can fit this, then C star reduced of n is maximal abelian. And I'm just going to write massa, so it's a maximal abelian subalgebra in C star reduced of G. And I don't know, Jakob, is this proposition due to you and the other people, or is that did that exist before? Okay, so I should probably attribute this to. So who is it then? Choda? Okay, thank you. Right. And in fact, I think you told me that this is not only maximal abelian, but it's in fact a Cartan subalgebra, right? And for non-C-star algebraists, this might seem a little opaque somehow why we care about these maximal abelian subalgebras, but actually this is a very strong structural statement to make that yeah, this guy is actually not just any old abelian subalgebra, but it's maximal abelian and it's even Cartan, so you get some sort of twisted groupoid and so on. And maybe Jakob will tell us a bit more about what that entails. Thank you.
Stock, are there some questions?
So yeah, just at the very beginning, saying that if you can find a finite index subgroup which is abelian, then it's maximal abelian. It's normal. I'm just wondering, is it true that any maximal abelian subalgebra then is normal as long as it's finite index?
Wait again.
So any maximal abelian subgroup of finite index is automatically normal? Is that how the proof works? That's a consequence. Does it? Okay. Okay. Is the proof easy or it takes a bit of work? Yeah. Okay. Cool. Thanks.
More questions? Maybe.
So it is, for me, it is more a remark than a question. So there are also similar constructions for Hopf-Galois extensions, and I was wondering if you know of some links between this C-star, so the situation in the C-star context and the Hopf-algebra context.
Similar in what way? Like what is the...
So, for example, if we take the group algebra CG and this normal subgroup N, then we can also construct the semi-direct product of using a two-core cycle in the similar way as we have there, and this construction can also be done with general Hopf algebras, and yes, and so that was what I was thinking about.
Yeah, I mean, I would think that this is a C-star algebraic version of this algebraic construction. I would strongly think, and I mean, this is the C-star G will be a compact quantum group in Voronovich sense. So probably this is like a C-star algebraification of the Hopf algebra theory. I would assume. Thanks.
Maybe I can comment on this. I actually had the same question. So it looks very much like this, and I guess that here this is the special case where the Hopf-Galois extensions are cleft. You see that the section you have here, I guess in the algebra world, would then correspond to what is called a cleaving map, and then you get these cross products So yeah, it really seems that this is the special case of cleft
That's that
Hopf-Galler.
stuff with the cleaving map. I never understood what
I would
that
say
was
the
about.
cleaving map should be S. Yeah.
Okay,
like-
okay. But it also does not have to be like a homomorphism or something. It's just a
Exactly. So there are these two cases. There is the case where this is trivial, where the cleaving map is an algebra map. And when it's not, it has to satisfy something else. So it has to be collinear and convolution invertible. And yeah, then you can still build this cross product.
Okay.
And show that there's an isomorphism. There are some comments.
Another question. So this group cohomology of H with coefficients in N, can you describe it in some way as a bullshit cohomology? Maybe of the group algebra?
that I do not know, honestly. I mean, it is some derived functor, right, in the usual way, but I don't know if that connects somehow to. I don't know. I don't know. Yeah.
When the group H is prime cyclic, you can do it. You can get the cohomology out of it, but I don't know if there is some further connection. Probably there is, and I'm not aware of it, but.
Maybe one more question. So what happens when S is actually a group homomorphism? Then this omega is trivial, but do you still get something interesting? Like it's not really a cross product, but like in algebra world, this would be a smash product then?
Yeah, I mean, here then just the cocycle disappears, right? And you just get a semi-direct product induced by the action. So it's not the Cartesian product, like it is interesting in that sense, right? And I guess then similarly for this, the C-star algebra would be a genuine cross product and not one of these twisted cross products. Yeah. So I guess that's again completely analogous, I would guess. With the
Absolutely. Okay, are there more questions maybe from the online audience? If not, then let's thank the speaker. Now there's a short break and then the main seminar.